This video is part of a series in which I describe how to implement a simple microcontroller core in System Verilog. In this video, I'll be walking through the Verilog code that implements simple instructions like the move immediate and the ALU instructions. In previous videos in this series, I described the finite state machine, the states of which are shown in this diagram here. Every instruction begins in the fetch state, and many instructions take only a single cycle, so they remain in the fetch state. But some instructions take 2, 3, or more cycles, and we'll go through this sequence of states before they return to the fetch state and begin the next instruction. We also have a start state and an illegal state. Here's the timing diagram for the execution of a typical instruction that happens to take 3 states or 3 cycles. So we can see the Verilog register called state moving from fetch to exec2 before returning to fetch for the next instruction. We also see that in the cycle preceding the instruction, that is before this clock edge right here, the program counter is fed to the memory. And then on the next cycle, the memory will produce a byte. It will fetch the opcode byte of the instruction. And then on the following cycle, that is the cycle following any fetch cycle, we will always load the instruction save register. An important combinational signal is this instruction signal here, which is an 8-bit signal that is the opcode of the instruction currently being executed. And that will be computed combinationally from the output of the memory and this instruction save register. Whenever the state is fetch, we are just using the output of the memory, and otherwise we're using the value that was saved in the instruction save register. So throughout the execution of this instruction, we have this signal here, this 8-bit signal being the opcode of the instruction that's being executed. And we also see the program counter, and so for many instructions the program counter will just stay constant throughout the entire instruction. For some instructions like call and return, we'll be loading it with something different, but that's typically what happens. And then on the clock edge, when the instruction starts, we'll be loading it from a previous value and thereby incrementing it. So we see it being incremented, and this is what it looks like for normal sequential execution. Here's the System Verilog code for the core module. This code is tested and working. For this video, I've eliminated some of the stuff we're not interested in. This enumeration right here shows the states of the finite state machine. The core module is clocked, so it has a clock and also a reset input. We can single step the module, and for that we have a single step button. This input right here reflects the value of that single step button. We've also got a number of outputs, and these will be used to drive the 2 7-segment LEDs. With these LEDs we can display a single byte, and we can select which byte we want to display by pressing various buttons. But that is handled outside of this module, so I won't talk about that. Here are the Verilog registers of this module. The most important one, I suppose, is the current state of the finite state machine. Here is the 16-bit program counter, and here is this instruction save register that I just talked about. We've also got a 16-bit stack pointer, and we've also got this MSB register, which stands for most significant byte, and that's used by some instructions that have a need for additional storage. And finally, we have 4 1-bit registers that contain the values of the condition codes that were produced on the last ALU instruction. In addition, we've also got a number of signals that are computed combinationally. This is probably the most important one. This contains the 8-bit opcode of the instruction that's currently being executed. On every clock pulse, we're going to be loading the state register. So on every cycle, we need to compute combinationally the value to load into that register. So that is the next state signal. So on every clock pulse, we'll load the state register with whatever we've set next state to. On most clock pulses, we'll also be loading the program counter. Typically, we just simply increment the program counter. So we need to set the next PC value to whatever we want to load into the program counter, and that would typically be the PC plus 1. And we don't always load the program counter. Some instructions will not be loading it during subsequent cycles. So we have this PC write enable signal. We'll raise that when we want the program counter to be loaded, and that is typically on every cycle. To do single stepping, we've got a clock enable signal that we'll be supplying to our other modules. And so this code right here will compute the clock enable signal. Whenever the single step button is pressed, we want to raise the clock enable signal for one cycle. So in order to do that, we've got one register, which is the clock enable signal itself, as well as a register to remember what the single step button was before on the previous cycle, so we can detect a transition from low to high. That's what this code right here does. When the single step button was previously not pressed and it is now currently being pressed, then we want to raise the clock enable signal for one cycle, and then on the next cycle it will be lowered. If we want to run at full speed and ignore the single step button, then we can change this value here to 1, and then the clock enable signal will be 1 at all times. And so everything will happen at the full speed of the clock. Now we have the instantiations of 4 different modules. So the core module contains 4 submodules: the memory module, the instruction decoder, the registers module, and the arithmetic logic unit. Now there are a lot of signals, and rather than talk about them by looking at the system Verilog code, I'm going to switch to these diagrams and show the signals. And the signal names in these diagrams are exactly the same as the signal names in the Verilog code. So for the arithmetic logic unit, which is purely combinational, we have 2 inputs, the A and B input, and we have the 8-bit output. We also have the carry input, and we have the carry output. We also have the sign, 0, and overflow outputs. The function code is a 4-bit code that comes from the instruction and tells the ALU module which operation to perform. Now I tend to name the signals to these modules with a prefix. In this case it's ALU, to show what module it is, and that will make things a little bit clearer later. So here you see the ALU signals. Here we see the register signals are prefaced with reg, and the memory signals to the memory module are prefixed with mem. So we've got the memory module here. This module takes as input a 16-bit address, and it produces a byte. So on every cycle, on every clock cycle, it will be reading a byte from memory. So the address goes in on one cycle, and then the output is valid on the next cycle. Our memory module has a 1-cycle delay when reading. We can also update the memory module, so we've got a clock and clock enable signal going in. Whenever we want to update the memory, we need to raise the write enable signal here. At the same time, we would supply the address of the byte we want to update, as well as the new value to store into that byte. So then the memory would be updated on the rising edge of the clock. Here we've got the registers module, and that contains the 8-bit registers. It is always providing the value of the registers combinationally. So at any point in time, we can see what is currently in the A register, or the B register, or the 16-bit XY register, or the 16-bit M register. And we can also select a register, so the register read address, which is 3 bits, goes in, and combinationally the value of the selected register is coming out. We have 8 registers, so the 3 bits form an address, if you will, with A being address 0, B being address 1, and so on, with M2 being address 7. If we want to update one of the registers, then we have some enable signals. We can either update one of the 8-bit registers, or the XY register, or the M register. So we have these three enable signals. The data going in is a full 16 bits, and that would be necessary for the updates to the XY or the M register. Whenever we want to update one of the 8-bit registers, we also have an address of the register we want to be updating. So the write address is a 3-bit address of one of these registers, and we would raise the write enable for the 8-bit registers, and the data that we want to store into the register would be in the low order 8 bits of the 16-bit input. And the fourth module that we want to concern ourselves with here is the instruction decoder. The value of the current instruction, this is a combinationally computed signal, is going into the instruction decoder, and combinationally it's computing a number of different outputs. The op type categorizes the instruction. So we have a number of different op types for the different types of instruction, such as the move instruction, the ALU instructions, the move immediate instructions, and branch instructions, and so on. We're also peeling out or identifying and outputting particular fields in the instructions. For example, the ALU instructions have a 4-bit function code. That's coming out here. The branch instructions have a 4-bit condition code, and that's coming out here. The add 16 instructions have a destination register and a source register coming out here. And then many instructions have a 3-bit destination register, and that field comes out in this signal here. And the move, the register move instruction, also has a source register field, and so that is a 3-bit field that's coming out in this signal here. So now we can move on down past the instantiation of these. Here we see assignments to these debug outputs, and so we're displaying the program counter. Well, we can only display 1 byte, so actually we're just looking at the low order byte of the program counter, but that's enough. Here we're looking at the current instruction that's being executed, and we're also able to look at the state as well as the next state. And then we have 2, which we call miscellaneous outputs, and usually we will be displaying the current value of the A register. This is always coming out of the register unit, and these signals give us the current value that's in the A register and the current value that's in the B register. And so we can take a look and see what's in the A register at any point in time. Now we get into the code that updates the registers. So this always flip-flop construct is not very long. It just goes down to here. And it resets things if the reset signal is high. We set our current state to the start state and initialize the program counter and the stack pointer to 0. We also initialize this instruction save register, but that's not really used. But if we don't have a reset, then we update the registers as shown in this code right here. As I mentioned, we always update the state of the finite state machine, and we set it to whatever we've computed combinationally with the next state signal. We update the program counter if and only if the program counter write enable signal is high, and then we set the program counter to whatever it is we've computed. So again, normally this would be the program counter plus 1. The instruction save register is saved, and it is set to whatever has just come out of the memory unit. So as I talked about before, whenever we are in the fetch state, we will be storing whatever just came out of the memory, and we'll be using that to compute the value of this instruction signal. And we also update the condition code registers. So we do that for ALU instructions and for the compare instruction. And so on those instructions, we'll need to be raising the condition code write in signal, and that will enable a write to these 4 1-bit registers, and we will always be storing whatever just came out of the arithmetic logic unit. The rest of the core module consists of this always comb construct. Here's where we compute the value of the instruction, and if we're currently in the fetch state, then we just use whatever came out of the memory unit. Otherwise, we use whatever has been saved in the instruction save register. Here I'm setting a number of defaults. So by default, we are going to supply the current program counter as the address to be read from for the memory unit. And by default, we will not be storing anything into the memory. When we store, we will by default take the data that comes out of the register unit, and that is appropriate for the store instruction. The next state by default will be the fetch state. Many instructions will just stay in the fetch state, so this is the default. By the default, we will be incrementing the program counter on every cycle, so we raise the program write enable signal and set the next PC to PC plus 1. For the register unit, we will by default not be writing any of the registers, so these are set to 0. The read address, we will use as a default the register source field, and that comes out of the move instruction, so that's appropriate for the move instruction. And when we want to write a register, we can use the destination field from the instruction, and so that would be appropriate for the instructions that write registers. For the register data input, we'll use whatever came out of the memory, and this is what we'll have to override for the move and move immediate instructions. For the arithmetic logic unit, we will use the function code that comes out of the instruction. So this is the signal from the instruction decoder here, and we'll supply that directly to the ALU's function code input. And for the 2 inputs for the ALU, we will supply the current value of the A and the B registers, and for the carry input, we supply the current value of the carry flag. The body of this always comb construct is basically some nested case statements. So here we see a case statement, and here we see a nested case statement. So we first look at the state, and then we look at the type of the instruction. And so for the state, we see the start state, we see the fetch state, and we see the other states, the execute state, exec2, and so on. And we go all the way down here. This handles the illegal instructions, and we basically, once we're in the illegal state, we stay there, and we don't update the program counter. So let's go back up here to the start state. Our defaults are good for the start state. By default, we will be updating the program counter and incrementing it. So it starts off at 0, and we increment it. And by default, we'll be going into the fetch state, so we stay in the start state for only 1 cycle. And our defaults for the memory are just fine. We'll be supplying the program counter as input to the memory unit, and we will be not updating, and so that's just fine for the start state. For the fetch state, we need to take a look at which kind of instruction we have. So op type comes out of the instruction decoder, and here we see the register move instruction, here we see the ALU instructions, and here we see the move immediate instructions, and those are the ones I want to talk about today. For the register move instruction, we will be updating the registers on the next rising clock edge. And so we won't be going into any others. We'll be going right into the fetch state for the next instruction. Or to say it another way, the move instruction will take only 1 cycle. So we don't need to update the next state at all. We'll go straight into the fetch state for the next instruction. But on that rising edge, we will also be writing to the register. So here we are raising the write enable for the 8-bit registers to 1. And we're supplying as our data input to the register unit whatever is coming out of the register unit. And so by default we supplied what came out of the memory, but we don't want to use that. We want to use whatever is coming out combinationally from the register unit itself. And what is that? Well, by default we're using the source field of the move instruction as the address. So whatever's coming out of the register unit will be determined by this field, the source register field of the move instruction. So on the rising edge of the clock we'll be loading the register unit from whatever just came out of it. The ALU instruction also uses only one state or one cycle, so we don't see the next state being modified here. So like the move instruction, we're going to be updating the register unit. We're going to be updating one of the 8-bit registers, so we raise the write enable for the 8-bit registers. We can't use the default for the write address. Remember that the 8-bit registers are numbered 0 through 7. We want to update the A register for all of the ALU instructions. So here we are setting the write address for the register unit to the address of the A register. And we're providing data to be written into that register as the data that's coming out of the ALU. So whatever the ALU is computing during the fetch cycle will be used on the rising edge of the clock to load one of the registers. And at the same time we also want to update the condition code registers, so we are raising the condition code write enable signal. Now the move immediate instruction is going to take 2 cycles, right? The move immediate instruction is an instruction that has 2 bytes. The 8-bit opcode is followed by an 8-bit immediate value. So we will set next state to exec state, and that will send us into the exec state on the following clock cycle. And here we see that the code for the exec state again is this nested case statement. So we're looking at the type of the instruction, and I'm showing the move immediate instruction here, but the other instructions I'm not looking at today. So normally we are incrementing the program counter and sending the program counter to the memory unit and fetching a byte. And so that's what will happen on this cycle here. As we move into the exec state, we will have data coming out of the memory unit. It's not an opcode for an instruction. Instead, we will be using whatever comes out of the memory and feeding it as input into the register unit. And so we will be writing to one of the registers. We need to raise the write enable line for the 8-bit registers, and we do that here, and that will cause a write to happen, and that write will happen on the rising edge that leads us into the fetch state of the subsequent instruction. So and also the address of the register we want to write defaults to the register destination field of the move immediate instruction, and so that's just fine. So that shows how these 3 instructions, the register move, the ALU instruction, and the move immediate instructions, are executed. Well, that concludes this video, and in the next video we'll take a look at some of the timing and see an example of executing these instructions. I will see you in the next video.